In this video, I'm going to go over in detail how I built my mini AI wildlife monitor. This video is going to be a long one, so let's jump straight into it by talking about the major components you're going to need for this project. I'll try to leave links in the description so where you can find them, but where you end up buying them from will depend heavily on where you're from. Starting off with the electronics, you're going to need a RasPi Pi Nano 2W, as well as a micro SD card, the Witty Pi 4 L3V7 with its accompanying parts, and importantly, the RasPi Pi AI camera, which uses the IMX500 intelligent image sensor that we'll be using to run our object detection model. And for this, we'll be using the standard to mini cable that comes with it. I highly recommend having some device to save the detections to externally, and I'm using this mini USB device with this tiny USB to micro USB adapter that sits inside. In my original video, I created this custom lithium-ion battery pack with two 21700 cells in order to power the device. That's a bit inaccessible to most makers, so for this new version, I made the box a bit larger so that we could fit some off-the-shelf lithium-ion battery holders. So the device can either fit three 18650 cells or two 21700 cells. And they could be mounted to this 3D printed battery mounting plate. It's also possible to find online some lithium ion or lithium polymer cells that already have the connectors. They are a bit more expensive, but it means you'll be eliminating the only soldering you'll need to do for this project, which is attaching the battery connector to the battery holders. To secure the batteries, we'll be using some adhesive Velcro strap. Onto the 3D printed parts. The files for this project are all available online and there'll be a link in the description. So the main components are the body and lid of the enclosure, that battery mounting plate, as well as the RasPi Pi mounting plate, an optional TPU gasket, which we'll get into a bit more later, the camera shroud that sits on top of the lid, and 4 clips that also act as hinges. There are quite a few fasteners to hold this all together. You'll need 8 30mm M3 bolts and nuts, 4 10mm M3 bolts, 4 5mm M2 bolts, and optionally 2 or 3 M2.5mm flat head bolts. Optionally, an additional M2.5mm bolt that we'll be using to create threads in our 3D printed parts. You'll also need a 3mm piece of acrylic cut to a 30 by 30mm square. As for adhesives, I'm using both silicone adhesive as well as an all plastics glue, and for mounting the box we can use a variety of straps, and in this new design I've also got some mounting holes that can accommodate some 6G self-tapping screws. As for tools, the main ones you'll need is a set of metric Allen keys, a Phillips head screwdriver, and always useful, a pair of needle nose tweezers. If you are going to be soldering together your own battery holders, you'll also need some solder and a soldering iron, as well as some heat shrink tubing to protect the joints. Alright, let's start off assembly by 3D printing our enclosure. Here I've printed the enclosure out of white PETG, which is a durable and easy to print plastic. It would be better to print it out of something like ABS or ASA like I've done with my larger boxes, but they require a fully enclosed 3D printer and are a bit tricky to print. After we've done our 3D printing, the next step is to pre-thread all of the screw holes in our enclosure. I find this makes later assembly a lot easier. So we can use the M3 bolts to pre-thread the holes for the mounting plate in the body of the enclosure, and then use the optional M2.5 screw to thread the holes of the RasPi Pi mounting plate and also optionally the battery mounting plate. We can pre-thread the holes on the lid of the enclosure for the camera with the M2 bolts. And again, this makes later assembly a lot easier when there's no other parts here. Once we've done that, we can begin the assembly by attaching the hinge clips to the lid of our enclosure. And for this, we'll need the 4 hinge clips, as well as 4 of the 30mm M3 bolts and the accompanying nuts. This step is a little bit fiddly. You'll need to thread the M3 bolts through the holes in the lid and through the clips out to the other side, and then using some tweezers, drop the nuts into the holder on the other side. Using your fingers to ensure that the nut doesn't drop out, use your appropriate Allen key to tighten in place. Tighten the bolt until the clip becomes really stiff, and then back it off a few turns so that the clip is now loose. Tightening it up first ensures that the nut has been pulled into the hole, but we don't want it to be over tight, so we back it off to loosen up the clip. It should be floppy. There's a space in the body of the enclosure for a gasket, And you can either print this out of soft TPU, like I've done here, or do what I did in the original video and use silicon sealant. And this has lasted on my original design for a long time. I haven't had too much of a problem, but it is a bit messy. And if you have the TPU filament, it's a lot easier to install. If you're installing the TPU gasket, you can do so by pushing in the corners first and then fitting the rest of the gasket in place. This will sit slightly below the surface, and you can use the lid of the enclosure to press it down flat. The lid of the enclosure has a little groove that will bite into the gasket, creating our watertight seal. We can now install the rest of the 30mm M3 bolts and nuts into the body of the enclosure, and this is what the lid will clip into. This is a bit easier than the lid. We just thread through the bolts and drop in the nut and tighten. We can now do a test fit by placing the lid onto the body of the enclosure and clipping it shut. Once secured, the lid should swing freely and be able to be opened from either side. There should be a little spring in the lid from where it's compressing the gasket, but it shouldn't be too difficult to close. And just like that, we've got most of the enclosure ready. We can now move on to fitting the Raspberry Pi and the Witty Pi 4 together and onto the mounting plate. To fit the Witty Pi 4 L3V7 and the spacers and bolts onto the Raspberry Pi Nano is a little bit tricky. Start by placing the Witty Pi 4 onto the header pins of the Raspberry Pi Nano, but press it on only very lightly at this stage. The Witty Pi 4 comes with a bunch of nuts, bolts and spacers. We won't need any of the nuts, so we can get rid of those. We'll take the spacers with our tweezers and fit them in between the Witty Pi 4 and the Raspberry Pi Nano, and then drop a bolt through the top. We do the same with all of the other holes. Once we've done that for all four, we can now press the Witty Pi 4 down tightly, and this will hold the spacers in place, but you still need to be careful at this stage as the bolts still could come out. Now we can attach this assembly to the mounting plate. Pre-threading these holes are important because the mounting bolts that came with the Witty Pi 4 are plastic and won't thread the 3D printed mounting plate by themselves. Start by loosely screwing down each of the screws and then go back and tighten them all. We've now securely attached our Raspberry Pi Nano and Witty Pi 4 to our mounting plate. To create a little window in our enclosure for our camera, we're going to use a piece of 3mm acrylic, and we're going to need to cut this into a 30 by 30mm square. The easiest way to do this is to score it with something sharp and then just snap it using the edge of a table. We can then sand it down to an exact size using the 3D printed shroud to test the fit. The shroud itself I've 3D printed out of black PETG, and this is just to provide a little bit of shade for the camera, but won't obstruct its view at all. To hold the acrylic window into the shroud, I originally used this all-purpose plastics glue first, but this stuff is pretty dangerous. It tends to create long streaks of glue, and if these get onto the actual acrylic, there's no way to get it off, and your window is basically ruined. If your acrylic comes with some protective covers, leave this on until the last minute. So you'll need to take it off on one side first to glue the window into the shroud, but then wait a few minutes for the plastic glue to dry a bit before removing it from the other side, and then use the silicon sealant to create a nice watertight seal. I think it would probably be fine if you just used the silicon sealant and didn't use the plastics glue. If you get the silicon sealant on the acrylic window, it's not too much of a big deal. It does come off a lot cleaner, but it won't hold the window in place quite as securely. On the lid of the enclosure, there's 4 locating holes which match 4 locating pins on the shroud. This is to ensure perfect alignment of the shroud on the lid of the enclosure. Here I do use the plastics glue again and put some into the holes on the lid just to make sure there's no way that the shroud's going to come off. But I also use the silicon sealant again just to make sure that there is a watertight seal between the shroud and the lid of the enclosure. Gently place the shroud on the lid of the enclosure and move it around until you can feel the pins on the shroud drop into place of the holes on the lid of the enclosure. Then you can press it really tightly and you might get a little bit of ooze out from the silicon sealant, but this is just fine. Don't be tempted to clean it up right now. Wait until it's fully cured, which will take about 24 hours, and then just simply cut it off. Trying to clean it up now will just make more of a mess. Okay, let's move on to talking about powering the device. The battery mounting plate has 5 holes in it, 2 for the 21700 cells and 3 for the 18650 cells. This enclosure can fit 3 18650 cells or 2 of the larger 21700 lithium ion cells. For this demonstration, I'm going to use two 21700 cells. To mount the battery holders onto the mounting plate, I used these flathead M2.5 screws. And you're going to hate me for saying this, but I have absolutely no idea where I got these from. I found a whole bunch of them in my loose screws container, and they did the job perfectly, but I cannot find where you can actually buy these from. You can probably just use a countersunk screw, but there's not much room between the actual battery and the bottom of the battery holder, so you need something that's quite flat. The screws are just there to hold the batteries onto the mounting board so that we can then attach the mounting board into the bottom of the enclosure. We'll next need to solder together the battery holders in parallel, positive to positive and negative to negative, and we'll then need to solder these to the included pre-crimped battery connector that came with the Witty Pi. So the crocodile clip helping hands that I've got there, you don't need to use these, but they do make your life a lot easier when soldering together these tiny little wires. So I pre-tinned the wires of the battery holder together and then soldered on the connector before slipping over the heat shrink tubing to make sure we don't short the terminals of the battery together. And we can do the same with the other side. And we have our battery pack completed. For demonstration purposes only, I'm going to be using these two 21700 unprotected cells that I have. Do not use these. You need to use the protected button top battery cells. These particular unprotected cells are not designed to be put straight into a device. They are for building into larger battery packs that themselves have battery protection. If you short the terminals of these batteries together, there is nothing stopping them from discharging a high current and overheating and potentially damaging themselves. The original UPS I was using for my large camera box specified to use the unprotected cells for some reason, and I'm not too sure why that is, but for this project, do not use the unprotected cells. I'm only using them here for demonstrative purposes, and I'll go back to using the battery pack that I created before with battery protection in it. And to drive this home, I've even contacted the manufacturer and made sure all of these battery holders don't actually work with the unprotected cells. They need the button cells to work. To fix the battery mounting plate into the enclosure, we're going to use the adhesive Velcro straps that you can just stick together and then cut to size. So with this Velcro, we've got the hooks on one side and the loops on the other, and we just need to peel off the backing and stick it onto the battery mount. Whenever I have two Velcro pads on something, I like to alternate and have one be hooks down and the other loops down. That way, there's only one way to orientate the board or the batteries and have it actually stick. So we're going to mount both down onto the battery mounting plate before taking off the backing and exposing the adhesive, and then placing this into the body of the enclosure and pressing it down to stick the other side of the Velcro into the actual bottom. But as I said, I'm not using these. I'm going to be using my original battery pack that I've already created. We can now put the RasPi Pi Nano and Witty Pi that we've already attached to its mounting plate on top and use the 10mm M3 bolts to secure it down. I like using these little dome head bolts as they're a bit nicer and they don't stick out as much as some of the other socket head screws. Pre-threading the 3D print makes this step a lot easier. We can now do a preliminary test and connect our battery to the Witty Pi, and we should see the D3 LED flash, and that's just the Witty Pi giving us a little heartbeat signal. We'll disconnect the battery before moving on. Moving on to the camera, which is another pretty fiddly step because of the rigid camera cable and the sort of awkward camera clips that RasPi Pi likes to use. We'll fold the ribbon cable over a few times so that when we put the whole thing into the enclosure, it'll sort of accordion out as we open and close the lid. And I kind of just eyeballed this step, pre-folding before putting it into the rest of the enclosure. But to actually mount the camera to the lid, we'll remove it for now and secure the camera in place with those 4 5mm M2 screws and screw the camera down into those pre-threaded holes. And just like the RasPi Pi, we'll loosely place each screw into the holes before going back and tightening everything down. We can then pull the little clip tab from the camera, place the ribbon cable in, metal side down, and then push the tab back in, securing the cable to the camera module. And we've completed the lid camera assembly. Now to put the two halves together, it's easiest to lay the lid flat down while trying to connect the ribbon cable from the camera to the RasPi Pi. Very carefully open up the tab for the camera connector on the Raspberry Pi Nano. This thing is very, very fragile, so don't pull on it too hard. Carefully insert the mini end of the camera cable into the camera port. This might take you a few goes. You need to make sure the little tab is pushed in on both sides and secure. But once you've done that, you can now plug the battery in around the camera cable. It is a bit annoying that the Witty Pi has its battery connector on the same side as the Raspberry Pi Nano's camera port, but we'll have to make do. Once we've done this, we can fold the cable over and put the lid on the body of the enclosure and clip the lid down. Once we actually have the camera cable in the Raspberry Pi and the lid secured, I haven't had too much trouble when opening and closing the lid. However, you might want to add a little bit of silicone or liquid electrical tape to the camera port of the Raspberry Pi just to make sure it doesn't come out. But with that all done, we've actually finished the assembly of our device. We'll talk a little bit about ways of actually mounting the device out in the field, and this mostly comprises of things that I've found at the local hardware store. So in terms of Velcro straps, you can find these sort of long-ish cable straps that are fairly cheap and easy to use. But if you need a longer option, there are various tie downs with little clips that you can find, and the little camera strap holes on the back of the enclosure can fit up to 25mm width and 2 to 3mm thick straps. A new addition is the 4 mounting holes on the back of the enclosure. And these holes sit completely outside of the enclosure, so if you drive them too deep, they won't actually puncture the inside. And you can use 4 6G self-tapping screws to affix the enclosure onto a flat surface or design your own mounting option. As for some general user information, the Raspberry Pi Nano only has one actual USB port, which is the one closer to the center. The one further out is actually just for power. And to charge the battery on the device, you need to plug a USB-C charger into the USB-C port on the Witty Pi 4. A blue light will come on when the battery is charging, and a green light on the other side of the battery port will come on when the charging is done. There are times when I've tried to charge the battery, especially when the Raspberry Pi is on. When using a normal USB-C charger, it doesn't seem to work, and you need to use a normal USB charger with a USB to USB-C cable. To actually power on the device, you press the little on button on the Witty Pi, and if you've already flashed the SD card and installed it into the Raspberry Pi, the boot up LED should start to flash. But we're getting a bit ahead of ourselves, and we'll get to the setup of the Raspberry Pi now. I'll cover a bunch of the details on how to set up your Raspberry Pi, including specific information for this device, but there are a huge number of guides and tutorials out there on general setup information for your Raspberry Pi if you run into any additional trouble. I highly recommend you just use Raspberry Pi's OS imager in order to flash the operating system onto the SD card. And to do that, you'll need some sort of SD to USB converter. Once you launch the imager, choose the Raspberry Pi Nano 2 as your device. As for which operating system to use, we're going to just use the full desktop environment. You could go down into Other and choose the Lite operating system. However, it does mean you need to install quite a few more things, and some features like auto-mounting USBs are not available in the Lite version, and so you'll have to do that manually. However, using the Lite version of the operating system means the device is a lot more responsive and less likely to crash. When using the full desktop environment, I have had some issues where the device becomes unresponsive or just stops working. So if you know what you're doing, I recommend just skipping straight to the OS Lite. But if you're just starting out, start with the desktop environment, and once you can get this all working, you can try to get it set up with the OS Lite, and I've got some additional instructions in my GitHub repo, which we'll talk about later on, if you're trying to set up with the OS Lite. However, for this guide, we're just going to use the full desktop environment. Make sure you have your SD card plugged into your computer via the SD to USB converter, and click Choose Storage and find your SD card. Before clicking Next, we're going to press Ctrl-Shift-X on our keyboard in order to set some additional options. I recommend keeping the host name as Raspberry Pi and the username as Pi, but I am going to change it here just to show you what else you'll need to change if you do change these options. You'll also need to set your Raspberry Pi's password here and make a note of what you choose. And you'll also need to set the SSID and password for a Wi-Fi network. Doing setup with your Raspberry Pi with a Wi-Fi network that your computer and the Raspberry Pi are both connected to makes setup a whole lot easier, especially because you can pre-set up the Wi-Fi network for your Raspberry Pi before you even first boot up. You'll also need to go to the Services tab and enable SSH. Once you've done that, you can click Save and then hit Next and then confirm that you want to use these options. You can now wait a few minutes for that to write to your SD card. Once that's done, take your SD card out and plug it into the SD card slot of your Raspberry Pi Nano. Boot up the Raspberry Pi and wait a few minutes to allow it to connect to your Wi-Fi network. There are various guides online about how you can find the IP address of your Raspberry Pi on your network. I just like to go to the home page of my Wi-Fi router, which most Wi-Fi routers also have, and you can usually view the devices on your network and what their IP addresses are. Once you find your device, note down the IP address. This is what we're going to use to connect to our Raspberry Pi. In order to set up and configure our Raspberry Pi, we're going to use SSH or a secure shell. If you're not familiar with this, you're going to need to become familiar if you want to work with Raspberry Pis. If you're using Linux or iOS, you can use the terminal. If you're using Windows, however, ignore all the other software and options that you see online and just use the Windows subsystem for Linux. This is a inbuilt Windows app. You will need to install it, but it's very quick and it is easily the best option. It basically gives you a full Linux subsystem right inside of Windows. You can search for the WSL program in your start menu, and when you open it up, you should be greeted by a little terminal like this. If you are on Linux or iOS, you can SSH by just putting your username @ and the host name that you set, which is by default Raspberry Pi. However, this does not work on Windows, and you'll need to put the full IP address that you found on your router's page. Type out yes that you want to continue connecting and hit enter. And type in your password that you set for your device. And nothing will appear while you do this. That's perfectly normal. Just type out your password and hit enter, and you should be connected to your Raspberry Pi. We're going to start by updating the config of our Raspberry Pi by typing out sudo raspi-config, and you'll be greeted by a little GUI, and you can use your arrow keys to go up and down. And we're going to go into interface options, and we're going to enable VNC, I2C, and serial port one at a time. So hit enter and then yes, and do this for all three options. Once you've done this, go across to finish and reboot your Raspberry Pi. Give your Raspberry Pi a few minutes to reboot and then SSH back in just the same as you did before. We'll now update and upgrade all the software on our Raspberry Pi to make sure it's at the most recent version. Type in sudo apt update and hit enter. And when that's done, do sudo apt upgrade and hit enter. And this will take a few minutes. If you come across a prompt, just type in Y for yes and then hit enter and it will continue. One more thing we're going to install at this stage is the software for the IMX500 camera sensor that is on the Raspberry Pi AI camera. This again will take a few minutes to install, and when we're done, we're going to reboot our Raspberry Pi again. We're going to connect back to our Raspberry Pi now and test out our camera, but we're not going to use SSH over our terminal. Instead, we're going to remote desktop in with VNC, which is one of the things we enabled. And to do so on our computer, we're going to download Real VNC Viewer. So just click download and then install the software on your computer. When you open it up for the first time, it might prompt you to create an account or log in. You can just close this window. You don't need to do this step. To connect to our Raspberry Pi, we're just going to type in just the IP address up at the top and then hit enter. And hopefully, if we've done everything right, we'll connect. We'll just click continue if this is our first time and put in our username and password. And then click OK. And then with any luck, we should see our desktop environment for our Raspberry Pi. Now the Raspberry Pi Nano, even though this is the second version, is still quite a bit slower than all the other Raspberry Pis and struggles a little bit over remote desktop, but we're only going to use this for this step in order to just test out the camera feed. So you just have to be a little patient. So what we're going to do is we're going to go over and click the terminal icon, and this will give us a terminal just like the one we were using before, but this is now just on the Raspberry Pi itself. Now, with everything connected on our Raspberry Pi, including the camera, we're going to test it out by typing out rpicam-hello -t -0, and this should create a little preview window of what our camera sees. And again, the RasPi Nano 2 will struggle a little bit to stream the video from the camera, and the frame rate will be a bit low, but this is just the frame rate that it can manage streaming the video footage over Wi-Fi with remote desktop. The RasPi Pi Nano 2 can actually record at full 30 frames a second. It's just struggling to stream it here. And with all this up and running, that concludes the basic software setup of our device. To close out of this, just click back on the terminal and on your keyboard press Ctrl-C. We use Ctrl-C to stop or close any programs we're running over the terminal. We're now going to set up our Witty Pi 4 L3V7 and install the required software so we can shut down our Raspberry Pi when the battery voltage gets too low. And we can also create a schedule script that will boot up and shut down our Raspberry Pi at different times of day so we can get it automatically waking up in the morning and shutting down at night. So we can go to the official web page for the Witty Pi 4 L3V7 and there'll be a lot of information there, as well as the commands we need to run in our terminal to download and then install the software. So again, we're going to SSH into our Raspberry Pi over the terminal. And just a little tip, if we right click at the top of our terminal, we can enable some properties. So if we go into options and enable the use of Control-Shift-C and V, so we can copy and paste directly into our terminal. And I would also enable the insert mode and the quick edit mode here, so we can kind of copy and paste things from the terminal as well. So that will allow us to Control-C copy the code and then Control-Shift-V to paste it into our terminal. So we need the additional shift when copying and pasting from our terminal. We then hit enter and this first line will just download the software and then we can install. This will install the software and all the other additional dependencies. After this, we'll reboot our Raspberry Pi, wait a few minutes and then SSH back in. If we type out ls and then hit enter, we'll see all of the directories or folders in our Raspberry Pi and you can see there are two Witty Pi and UWI that have been downloaded and installed from the previous step. If we type out cd Witty Pi, then we can enter the Witty Pi directory, type ls, and we can see all of the scripts and software for our Witty Pi. We can now run the Witty Pi main script, and this gives us a command line interface to set up and configure our Witty Pi. It'll show some stats here, like the voltage and current use, and whether or not the battery is charging, the time on the Raspberry Pi, and the time on the Witty Pi, which hopefully will be synced here. If they're not synced, you can synchronize with the network time and write the system time to the RTC by just typing out the numbers and hitting enter. There's a whole lot more information on the Witty Pi 4 manual on how to set up a whole bunch of different things. And it even shows us how we can activate and connect to a web app version of that command line interface if you find this a bit easier to use. The URL here contains Raspberry Pi, which is the default host name, though I've never really gotten this to work and I just put in the full IP address for the Raspberry Pi while keeping everything else the same. If you're like me and you've changed the username for your Raspberry Pi, you'll get this message when you connect to the web page. This is saying that it can't find the Witty Pi 4 software because, as you can see, it's looking under home/pi, which is the username. For me, that would be home/Luke, and so we actually need to change this in the config. It's a bit annoying that it doesn't do this automatically, but we just need to go to the UWI folder, open up the UWI config, and then change the file paths here. We only technically need to change it for Witty Pi 4, but I'm going to go ahead and change all of them, and then we can hit Control X on our keyboard, Y for yes, and then enter to save. I'm going to rerun the diagnose script just to restart that web page server, and hopefully everything should refresh and we'll get all of the information. Now in the manual, it tells us how we can set up a whole bunch of things, including the scheduling of the on and off times for our Witty Pi. Now the way the Witty Pi does this isn't great in my opinion. The easiest way to set it up is by going to their website for the script generator. The way you create a script, you need to first select a startup time and date. This could be any time in the future or the past, which is the time when the script will first run. And if you want this to run indefinitely forever, there's no way to set that up. You just need to pick a end time and date that is really far into the future. So these two times and dates just specify when the schedule script will first run and run until. To actually create the script, we need to add some states, and these define the on and off times for our Raspberry Pi. In my case, I want it to run during the daylight hours, which is why I set the start time at 7:30 in the morning. And then in my states, I'll say the on time is 12 hours and then the off time is 12 hours as well. So at 7:30 in the morning, our Raspberry Pi should boot up, run for 12 hours, and then shut down. After 12 hours of being shut down, the Witty Pi will boot up our Raspberry Pi again for another 12 hours and continue on this cycle until the end date, which is in 10 years. You can add as many of these states as you want. So maybe we don't want it to run all day. Maybe we just want it to run for, say, 4 hours in the morning and then be off for 2 hours during the day and then be on for another, say, 4 hours and then shut down overnight. So you can see here under diagnose, it'll tell you what the period of your schedule is. Yeah, I've just made it 1 day. It doesn't need to be 1 day. Once it gets to the end of the states, it'll just loop back to the start and keep going from there. Once you're happy with your schedule, copy it to clipboard and then go back to your Witty Pi interface, and next to schedule script, click set and then paste your script into here and press OK. Now wait a little while it updates, and you should see next to schedule script, it should now change to in use from not in use. You should also see the next shutdown and next startup times change to hopefully reflect what you've defined in your schedule script. To further confirm that your schedule script is being used, under the Witty Pi directory, it should have created a schedule.wpi, which should contain your schedule script. And just like that, we've set up our Witty Pi and created a schedule, boot up and shut down time for our Raspberry Pi. At this stage, you're ready to write whatever code you'd like to get your device doing whatever you'd like it to do. I have a whole video on how to set up and use the Raspberry Pi AI camera, including training your own model and exporting it for the Raspberry Pi and running some of the test scripts that Raspberry Pi has created in their Pi Camera 2 library. However, I have spent some time creating a whole repo for my particular device that you can set up and run on your device straight away. So you'll need to go to my GitHub repo, Mini AI camera, and you can see here I've got all the Python scripts, bash scripts, and even an example network that I have exported for you. That is a YOLO V8N model trained on the Coco dataset. And we can now go through the setup for this code base. We have to install a few extra things to get my code up and running. Unfortunately, we need to install a few of the libraries system-wide, as the Pi Camera 2 strongly recommends and basically outright tells us that we need to install Pi Camera 2 at the system level and not to install it via pip in a virtual environment, which is a bit annoying, but it means we need to install some other libraries also at a system-wide level. One such library is the OpenCV library, which you can install here. We've already installed the IMX500 camera software, so we don't need to do that again. But after we've done our installs, we can reboot. Now that we've prepared our Raspberry Pi, we can git clone the software. So do so under the documents directory and wait a little while as it all downloads. We can enter the Mini AI camera directory and you can see all of the code and scripts should have downloaded here. We also have the included YOLO V8N model, as well as the labels for Coco, which is the human readable class descriptions. And you can see in the Coco dataset, there are a whole bunch of object classes. We can now create our virtual environment for our code base and install the requirements. Annoyingly, there is only actually one additional package we need to install, but Raspbian doesn't like us installing pip packages outside of a virtual environment, so we need to include that, making sure we're also including our system-wide packages and then installing the requirements. Once that's all done, if you're like me and have changed the username from Pi, you'll need to enter the data logger script and change the path from Pi to whatever your username is. This data logger script is what we'll run when we want to run the code. It'll enter the code directory. It'll put our Raspberry Pi into power saving mode, so it'll use less power, activate our virtual environment, and then run the detector data logger code using the config information from the config.json file. If we have a look in that config.json, you can see I've defined a bunch of values, model file path for our IMX500 neural network model, the associated labels, the confidence threshold for our model, a parameter called IPS, which is inferences per second. So this is how often we'd like to process our detections. So if we have the camera running at a full 30 frames a second, we might not want to process 30 frames a second worth of detections. And then LPS, which is logs per second, which is how often we want to save the images when there's been a detection detection and also save the detection data as a JSON. So the camera might be running at 30 frames a second, but we're only looking at detections at 10 frames a second, but we don't want to save images 10 times a second or log detections 10 times a second because that might be a bit too much. And also the Raspberry Pi Nano might struggle to save frames that quickly. We can also create a device name, which will be used when it's saving files. And we also have 3 parameters: save video, save images, and save data. If we want to save video when we have detections, save detection images, and save the detection data JSON. I don't recommend doing both save video and save images, as it might overwhelm the Raspberry Pi Nano a bit. We can also tell it to draw bounding boxes over the images when there's been a detection, and auto select media tells our Raspberry Pi to automatically try and find a USB device in the media directory, which should hopefully auto mount our USB to. So we don't need to change anything there now. You can go into the get args script, and you can see there's a whole bunch of more arguments that you can set, which we'll get to a bit later on. To make our script runnable, we need to use this chmod +x data logger, and we can now do a little test by running that data logger script. It'll take a little while to first run, and if this is the first time you're running this script, it'll take a little while for the Raspberry Pi to load the model into the actual camera. But on subsequent runs, this actually gets faster and faster. Once we've got it running, we can now point it around at different things. Here I'm just pointing it directly at myself, and you can see it's detecting me. It's got the confidence as well as the bounding box information. So it would be a little annoying if we had to run this script manually every time our Raspberry Pi booted up. So instead, we can create a service via a service script, which will get run every time our Raspberry Pi boots up, and we can configure it to tell it what to do when it boots up. And in our case, we want it to run our data logger script. So there is an example data logger service file, and if you've changed the username for your Raspberry Pi, you'll need to change it here in this script as well, and Control X, Y, enter to save. We then need to copy this to the correct location on our Raspberry Pi, and then we need to reload the system so it can find our new service script. And then we enable our new service. And at this stage, if we reboot the Raspberry Pi, it will now run our code. However, we can start it up straight away by using the start command. But once it does, we can use the status command to make sure that it is active and running. So here, enabled, and it is running. So all good. And we can just hit Control C here. That won't stop it from running. It'll just get out of this status window. Our service script also creates log files for those outputs we were seeing before. So we can go into that and see what's going on. That is saved in the var/log directory. You can see here data logger error and data logger out for any errors or just normal outputs. We can go into the data logger output to see what's going on. And we can see just the regular startup sequence. If I now point the camera at myself, exit out of this log file, and then go back in, hopefully we should see that it has changed. It won't update while we're in it, so we need to exit and go back in, and we can jump to the end of the log file by using Control-Shift_ and then Control-V, so that will jump to the end, and you can see we have our detections of me and also my phone that I've been using to film with. And again, we have the confidence values for both and the bounding box locations. And of course, this whole time, it was also logging the images and detection data to the USB so that we can review our detections at a later date. One last feature that I'd like to show you is how to enable valid classes. What this allows us to do is specify only a subset of all of the outputs of our model for our code to actually pay attention to. So our Coco model can detect a whole bunch of things, but a lot of those things we might not care about. So we can create a separate valid classes text file, and we can just enter one line at a time the classes that we actually want our detector to pay attention to. In my case here, I just want the bird class. So I'm just going to type bird on a new line and then Control X, Y, enter. You can go into the Coco labels like I showed you before if you want to know all the possible things that we could detect with this model. Once we've done that, we now need to enter this into our config file and just add a new line, same as before, in quotation marks, valid classes, colon, and then the file path of our valid classes text file, and then a comma at the end as well. You need to make sure you format this JSON correctly. Using a proper text editor does help here instead of Nano. We can now manually run our script, making sure we stop the service from running before we do this. We should see, if I point the camera at myself, nothing will happen. However, if I point it at a bird, we will now get some bird detections. And for testing here, I'm just pointing it at a picture of a bird on my monitor, and we can see all the detections there. So once you stop the script here, make sure you go back and enable or restart the service to get the data detection service back up and running. And just like that, we have our mini AI bird detector in this case, ready for deployment and testing. There's a lot of things I haven't covered here and how to get this up and running. If you face any issues, you can find my Discord server in the link in the description, which is where you can get help for this project. Alright, so after all that, let's make sure our batteries are charged and we're ready to deploy our device outside. I've just been strapping the device to a tree in my front yard where we usually have some birds hanging around. As I mentioned in my first video, the battery life on this device is about 18 hours. So for 12 hours a day operation, it lasts for about a day and a half. And how I usually use it is I set it up in the morning and then at night after it's shut down, I take it back inside and plug it in to charge. One issue with the Witty Pi 4 is that its max charging current is only at 1 amp, and as my battery pack is 10 amp hours, it takes about 10 hours to charge the device from completely flat. As I also mentioned in the first video, the device uses about 2 watts of power while running, and so we can do a quick calculation and find that over 12 hours we'll use 24 watt hours of power, and for the Witty Pi charging at 1 amp at around about 4 volts, that gives us about 4 watts of charging power. So from that we can conclude that it will take about 6 hours to charge 12 hours worth of battery usage. That's really not ideal, and there were some suggestions in the original video to try and incorporate solar charging into this device. One main issue there is that there really isn't that many good off-the-shelf solutions for solar charging devices like this. I've had this same exact problem with my larger boxes. If you've been following along, you'll know about that, but the main issue I've been having is that in order to provide power for a device that consumes 2 watts continuously, we actually usually need to use a solar panel that's much larger, something around 20 to 30 watts, in order to make sure that batteries are always charged and we don't have any downtime. While the Witty Pi could power the Pi and charge at the same time, consuming about 6 watts. Assuming that we get max 6 hours of direct sunlight a day on our solar panel, that still leaves us with another 6 hours during the day where we'll get no sun and all the power will come from our battery. Now, if you do the maths, this just about balances out for a completely sunny day. However, if you get anything other than a completely sunny day, your batteries are going to eventually become flat, and it doesn't matter how large your battery is, if you're not able to produce a day's worth of power on average every day, your battery will eventually go flat. And that's a real problem I've had, not only with the larger devices, which consume about 5 watts, but even with these smaller devices. Because of this, on our larger devices, we've actually kind of gone all out and commissioned the development of a carrier board for the Raspberry Pi, which has a whole bunch of features, one of which is high power MPPT solar charging of large batteries. So in this box here, I've got a 60 watt solar panel and a 220 watt hour battery that can power this device for 48 hours. However, this charger can charge up to 10 amps, and my battery pack is a 6S battery, so that's 10 amps at about 25 volts max. That's potentially up to 250 watts charging. And compare that to the 4 watts of charging on the Witty Pi, and it doesn't really compare. Now, of course, this 60 watt solar panel is not going to produce that. However, we can also connect this board to a large lithium iron phosphate battery, as well as up to a 120 watt solar panel. Now, as I said, this board does a whole lot of other things and is quite complicated to program the firmware on there, and I've currently got it set up specifically for our use cases that we're currently developing. But because we've had a lot of interest from people wanting to use this board, some friends and I are developing a much simpler Raspberry Pi hat that has the exact same solar charging on board, specifically for the lithium iron phosphate batteries. What this should allow you to do is power your Raspberry Pi projects continuously, even when they're out in remote locations. You can connect a truly massive lithium iron phosphate battery, and by connecting up to a 120 watt solar panel, you should have no problem keeping your Raspberry Pi projects alive 24/7. I'll be posting more updates about this on my YouTube channel, so let me know in the comments below if you'd be interested in seeing more about this. In any case, that's all I've got to say for this video. If you have any questions or comments, leave them below, or you can post in my Discord server. Thanks for sticking around to the end, and I'll see you next time.